Okay, welcome back. Let's look at this next definition here. We'll try to make sense of this. This is an important one. We're going to be talking a lot about pivot positions and pivot columns and free variables and such throughout the class. So, first of all, let's read this and then we'll maybe look at an example. This says, if there is a reduced row echelon matrix equivalent to A, row equivalent to A, with a leading entry in row I, column J, we say that IJ is a pivot position of A, and that column is a pivot column. So let's look at something that's not actually in echelon form at all. Maybe the example from last time here that wasn't in row echelon form because the leading entries are not to the right of the ones above it. So the question is, what are the pivot positions of this matrix A? Well, what this says is if that there is a reduced row echelon matrix row equivalent to A, well, we can get one that's row equivalent to A. Remember, row equivalent means you can be transformed into the other by a series of these row operations. So if we just like switched the positions of this row and this row, that should do it, right? If we do like row 1 and swap that with row 3, that's going to give us another matrix, which is not the same matrix as A, that now has row 3 moved into row 1, and row 2 is unchanged, and row 3 is now what row 1 used to be, like so. Now this is now in reduced echelon form, and the pivot positions in this, the position of the leading entries in this are here, and the row 1 column 1, row 2 column 2, and row 3 column 3. So where are the pivot positions in A? Is it here, here, and here? No, because there isn't a reduced row echelon matrix with pivot positions in these locations. It's where they are in the reduced echelon form version, which is here. So yeah, we could say in row 1, column 1, and row 2, column 2, and row 3, column 3 are the three pivot positions of A, even though they're not leading entries in A. So that's what a pivot position means. Now later in I think 1.4, we're going to see that every matrix is row equivalent to a unique reduced row echelon matrix, which means that you don't have to worry about there being some other sequence of row operations that would give you a reduced row echelon matrix with leading entries in some other location. It's always going to be in the same spots. So we can talk about the pivot positions because there's only one reduced row echelon matrix that defines where the pivot positions in A are. But we'll see why that is later. Okay, now where the pivot positions are is really important in telling you about the existence and uniqueness of solutions. So we have this theorem 1.2, which has a lot of stuff in it. The goal of this whole next page is sort of going to be to understand theorem 1.2, because this is going to get used throughout the class to describe all kinds of stuff. So let's look at example 3 here. Suppose each of the following are augmented matrices for a system. Is each consistent? And if so, how many solutions does it have? So first of all, maybe we can just notice where are the pivot positions. Like this is already in reduced echelon form. So wherever the leading entries are here is where the pivot positions are. So we have that. And anyways, let's answer the question. Is the system that this augmented matrix represents consistent? And if so, how many solutions does it have? Well, if we just translate this to equation form, it just says 1x1 plus 0x2 equals 2, and 0x1 plus 1x2 equals negative 7, which basically just tells you that there is one solution. That solution is 2, -7. Okay, let's look at B. This is in echelon form because the leading entries are to the right of the ones above it, but it's not reduced echelon form because they're not ones, and there's also this 7 here. Keep that in mind. So let's just go ahead and translate this to an equation. There's only one variable here, so this is just going to be -5x1 because there's only one column in the coefficient part of this. -5x1 equals 7, and 0x1 equals -3, and 0 equals 0. Now, is this consistent? In order to have a solution of this, like you could make the first one true because x1 could be -7/5, -1.4, and that's fine. But that's not going to make the second one true. There's no way to make 0x1 equal to -3. So this automatically has no solution. And the way you can tell that it has no solution right off the bat is that this row basically says 0 equals -3. So if there's a pivot position in the rightmost column, that means you have something non-zero on the right side of the equals. That's just a constant non-zero number. And if that's the leftmost non-zero thing, that means everything on the left side of that must be 0. So the equation is already of the form 0 equals a non-zero, and that is always false, and that means your system is inconsistent. Okay, let's look at C. This one's a little bit more complicated. We already talked about in the last video how you can tell this is already in reduced echelon form. So there's no more like row reduction or Gaussian elimination that you can do. So let's just translate it to a system of equations. We have 1x1 plus 4x2 plus 0x3 equals 0. And the last equation is just 0x1 plus 0x1 plus x3 equals 3. Now notice in this case, none of the pivots are in the rightmost column. All of the pivots go along with one of the variables on the left side of the equations. Something else to notice is that there is x2, this variable here that doesn't have a pivot. And what that means is that you have this equation, like that 4x2 is not a leading entry, so that means there's got to be another variable in this equation. And because it's in reduced echelon form, we know there's no other equations that have x2 in them. So basically, this is the only equation with x1 and x2. It's got to have x1 and x2. And that means this equation has an infinite number of solutions because it has two variables. And no other equations are going to restrict x1 and x2 because everything in the bottom part of this has to be 0. So that automatically means having this non-pivot column here that goes with the variables in the coefficient matrix means there's going to be an infinite number of solutions because you're going to have this equation that has at least two variables that goes with that row. So yeah, let's think about what some solutions might be. You can pick anything you want for x2. Maybe x2 could be 1. That means x1 is going to have to be -4, and x3 always has to be 3. Another solution might be, let's see, if x2 is 0, x1 would also have to be 0, x3 must be 3. We could also say, what if x2 is 7? x1 is going to have to be -28 to make that work. So this is consistent with an infinite number of solutions. All right. So let's look at the definition of basic variables and free variables. So variables which correspond to pivot columns are called basic variables, and any non-basic variables are called free variables. So for example, in part C here, there's a variable x2 here that does not have a pivot in that column. So we say x2 is free. Now, when you solve for all of the variables in terms of the free variables, you have what's called a parametric description of the solution set. So right now, this isn't like directly telling you some solutions. I kind of had to do a little work in my head to like figure out what are the x1s that go with x2. It's kind of better if we can get a parametric description of this solution set. So let's do that. We want to solve for all of the variables in terms of the basic variables. So all the variables are x1 and x2 and x3. Well, what can we say about x1? If we just move the 4x2 over to the other side, that first equation says x1 equals negative 4x2. And x2, that's just x2. x3 we know is 3. So we're basically writing the equations we have to give us a description of x1 and x2 and x3, but you write it all in terms of the free variables. You could also write this using like set builder notation. We could say the set of all points of the form negative 4x2 x2 comma 3 such that x2 is any real number. If you haven't seen this kind of notation, we'll cover it more later, but that's another way to describe the solution set. But here you can see you can take any number you want for x2, like 1 or 0 or 7, and plug those in here, and the result would be the x1, x2, x3 solution that you get. Okay, so that's parametric descriptions of solution sets. Now let's look at example 4. We're going to reduce this augmented matrix to reduce row echelon form and then describe the solution set. So we're going to use the Gaussian elimination operations but in matrix row operation form. The first thing to do is to make it so the top equation or the top row has an x1 coefficient of 1. So you could do that by like multiplying this whole row by negative 1/3, but then you're going to have some ugly fractions, and I don't want to deal with fractions. So instead we can swap row 1 and row 2 to get that negative 1 in that first position and avoid the fractions. Now there's a negative 1 in that top row. Maybe we can make that become a positive 1 by doing negative 1 times row 1. So basically multiplying both sides of this equation by negative 1. Okay, now the next thing to do is to clear all of the x1 coefficients below this like leading entry position where you have that 1x1. So we can do two multiplacements operations. Row 1 is unchanged. Row 2 is now 4 times 1 plus negative 4 is 0. 4 times negative 4 plus 16 is also 0. 4 times negative 1 plus 1 is negative 3. 4 times 5 plus negative 5 is 15. And in row 3, we have 3 times 1 plus negative 3 is 0. 3 times negative 4 plus 12 is also 0. 3 times negative 1 plus 1 is negative 2. And 3 times 5 plus negative 5 is 10. So at this point, you can tell we're getting somewhere. We're getting closer to being in row echelon form. Strictly following the strategy from 1.1, we should be trying to get an x2 in this position here, a 1 times x2 term, but that's not really possible because below here there's no other x2 terms, and we don't want to use this negative 4x2 from the first equation because that would mean involving the x1 where we don't want it. So we're going to skip ahead to x3 and making this term here become 1x3. To do that, we're going to scale row 2 by negative 1/3. Like so. And at this point, we can add multiples of this row without messing up the x1 and x2 terms in the other rows in order to clear away all the other x3 terms in the first two rows. And that's going to be using the multata placement operations. Row 2 plus row 1 to replace row 1, and also 2 row 2 plus row 3 to replace row 3. Oops. This was supposed to be a 5 here. Row 3 becomes 2 times 1 plus negative 2 is 0. 2 times negative 5 plus 10 is also 0. So, hey, look, we are now in reduced row echelon form. We can see where the leading entries are in each row, except for row 3, which does not have a non-zero entry. And that means that the places where these leading entries appear are where the basic variables are in the equation, which are x1 and x3. And x2, which does not have a pivot, is going to be a free variable. So let's write this as a system of equations. And that shows you how to write it in parametric form, because we don't really need to bother with the 0 equals 0 equation. That doesn't tell you anything. But we could solve for all the variables in terms of the free variables. The first equation here gives you x1 in terms of x2 is x1 equals 4x2. And x2, because it's a free variable, we just say is equal to x2. And x3 is negative 5. You could leave it like that, or alternatively, you could say the solution set, described in set builder notation, is points of the form 4 x2, comma x2, comma negative 5, such that x2 is any real number. Either of these are fine. Okay, at this point, we are ready to read the existence and uniqueness basics theorem here, which is going to be a really important one to understand why this theorem is true. We're not really formally proving it because I think this is one where examples help you understand it better than a proof would. Now, the first thing it says, part 1 here, is a system is consistent if and only if the augmented matrix does not have a pivot in the rightmost column. So let's look at some systems that do not have pivots in the rightmost column. For example, this one in example 4 right here. The pivots are all in the x1 and x3 columns. And that's true in the original matrix, the original augmented matrix as well, because the definition of pivot positions of this is not where the leading non-zero entries in this are, it's where the leading non-zero entries are in the reduced echelon matrix row equivalent to it. And so none of these are in the rightmost column. And having an augmented matrix that does not have a pivot in the rightmost column, that basically means the system is not equivalent to a system that has 0 equals non-zero. In other words, this system is not equivalent to a system that is always false. So, yeah, you can always get your variables equal to something if all of the equations you have variables on the left side, basically. Here's some other examples. Part C here. This is one that, again, has no pivot on the right. Here's one that does have a pivot on the rightmost column with part B. That gives you 0 equals non-zero, and that's why that one was inconsistent. Exercise 1, the warm-up we did. Here is an example where there is a pivot in the rightmost column. That means this original system is inconsistent because it has the same solution set as this other system that says 0 equals -9, and that's impossible to make true. Okay, let's look at part 2 here. This says if the system is consistent and there is at least one non-pivot column in the coefficient matrix, then there are an infinite number of solutions. We saw that here this non-pivot column goes with a free variable, and that means you must have an equation that has a basic variable and a free variable in it, and that equation is going to have an infinite number of solutions. In other words, you can pick anything you want for the free variable and you'll get another solution. One that doesn't have a column without a pivot in the coefficient matrix is like part A here. All of the variables are basic variables. That means all of these equations just have one variable in them, and it's of the form like x1 equals a number and x2 equals a number, and that just describes your unique solution. And that's basically what part 3 says. If the system is consistent and there are no non-pivot columns, then the solution is unique. Okay, so yeah, this is an important theorem. All 3 parts of this we're going to be using pretty regularly. And it is important to understand why these things are true. And it's also important to get practice just using the theorem. Like once you believe the theorem, just citing it to make conclusions. Because that's a main thing in math, is using the knowledge that you already have to build more and more complicated things without necessarily looking into the nitty-gritty details all the time. Here's an example of what I mean by that. Like, so you're going to have some true or false questions where you're going to have to think about this theorem and other things you've learned about pivot positions and such. And one question is number 19. This says true or false. If an augmented matrix has a row equal to 0, 0, 0, -2, then the system is inconsistent. Now, spoiler alert, this is true. The system is inconsistent because, well, one way to think of it is just thinking about what that equation means. It means 0 plus 0 plus 0 equals -2. So, yes, the system is inconsistent. And that's great to think of it that way. But it's also good to know what theorems say about this, just to get used to studying the theorems. So you could also say this is true because the augmented matrix has a pivot in the rightmost column. So the theorem 1.2 part 1 says the system is inconsistent. So both of these are great. And it's good to do as many questions as you can, thinking about it both ways, like about the concrete example that you have in front of you, and also what do the theorems in the section say about it. So yeah, in the homework you're going to get some practice thinking about pivot positions that way. Also, you'll get some concrete examples here where you actually describe the solution set. Also, some more abstract ones later here. We're going to branch out a little bit and figure out slightly more advanced things. Anyways, good luck with all that. I will see you later.